the following statement. So, rate of change with respect to time of velocity of a coasting motorboat is proportional to the square of its velocity. So, kind of like the Newton's law of cooling, we can write this out in algebraic form. What it means is a rate of change, a time rate of change. And it's rate of change of velocity, little v. So, rate of change of velocity with respect to time is what?
kv squared.
Proportional to the square of its velocity. Yeah. Okay.
Question mark.
Yeah, and this is a perfectly good differential equation. Now, we saw one, the integrable. I have to say that so slow, or I'll stumble over the syllable. But the integrable differential equations are ones that only involve the independent variable. So, like if it was dv dt equals kt squared, I can differentiate both sides with respect to t, or differentiate this with respect to t to come up with my function. This, on the other hand, only has the dependent variable v. There is no mention of little t in there. We'll see what this is called as a homogeneous differential equation. It only involves the dependent variable. Anyway, we're not going to solve that right now. But it happens that this is also the same differential equation, well, just different name, that describes the rate at which the height of something changes with respect to time. So, instead of velocity, if it was height, just under gravity, if I drop something, the distance it falls is, the distance that it falls is proportional not to the time it's been falling, but to the square of the time it's been falling. Right? That was another thing that someone, don't ask me how they do this, but they measure that, see an apple fall, and they go, wait, it's not falling equal distances each moment. It's not proportional to the time it's been falling, proportional to the square of the time it's been falling. Someone noticed that.
This was even before stopwatches.
Yeah, apparently, allegedly, the myth goes that it was measured by measuring it against its heart rate. And
Really?
How do you even?
Maybe you got really excited though as it was falling.
No, but it was more of a pendulum. I think that one was with the pendulum, seeing the rate at which a pendulum swings or something. But anyway, so this is all it asks for. It doesn't ask us to solve that, although it's not terribly hard. It's an example of a separable differential equation. It can be solved using integration. Let's look at the back side. And number 3, how about part A? So we got this, it says find a function that satisfies the initial value problem. So remember, initial value problem is a differential equation. A differential equation together with some condition of the function that it satisfies. Okay, so taken together, that's what we call an initial value problem. So this is again one that's integrable, meaning it only involves the independent variable x. There is no mention of y anywhere else. So we can solve for y by integrating that function, that expression, 1 over root x plus 2 with respect to x. All right. So, yeah, some people are thinking, oh God, is this a u substitution? How do you do this? Yeah. U substitution, yeah, you can, for a moment, if you just let a change of variables, let u represent that quantity x plus 2, then it would just be 1 over root u, and du dx equals 1, and we can also write du equals dx. So they're interchangeable as far as variables, exact same rate of change. So this integral would just turn into 1 over root u, which is u to the negative 1/2. We saw this. And what is this?
2 square root.
2 square root of u plus some constant, which, again, resubstituting that quantity for u would just be 2 root x plus 2 plus some arbitrary constant. Now, to recover the value of that constant, we need to use the initial condition. Yeah? So we know that y of 2 equals negative 1, and that is what allows us to find that constant. So subbing 2 for x, 2 times square root, 2 plus 2, we're putting 2 in for x, 2 root 4 plus c has to give us -1, and that results in an equation that only involves c as an unknown. So what do we get there?
-5.
-5. All right, so our function y of x is equal to 2 root x plus 2 minus 5. Something like that. Okay? All right, anybody on B recognize this as how to integrate this?
Trigonometry.
Pull that 10 out.
Right. Yeah, if you pull out that constant, if you pull out that 10 from the integral, it'll be 1 over x squared plus 1 dx. And what is this? Tangent inverse, inverse tangent, right. 10 tangent inverse x plus some constant c. And then we use the initial condition that y of 0, if I plug that in on one hand, y of 0 is going to be 10 tangent inverse of 0 plus c. On the other hand, we know that it equals 0, so I set it, oops, equals 0, not c. And what's tangent inverse of 0? Yeah, 0. Tangent inverse function contains 0, 0. Since tangent of 0 is 0, tangent inverse of that 0 is 0. Switch. Okay? So this is 0. And so 0 plus c, that just gives me c equals 0. So in this case, the constant is 0, exactly. So our function, our solution to that problem, y of x equals 10 tangent inverse x. All right, good. So the rest of the solutions will be up online, and you can check your work there. Oops. Okay, so one more now. When we talk about integrable differential equations, one example of a physical example of derivatives and integrals is motion, right? I heard someone say rectilinear motion, a word you sometimes rarely hear, but it's only in math when you hear it. Rectilinear motion. And that just means motion in one direction only. So no curvature, no free space, no space curve, but just motion, which means you can go in one direction or back. Okay? That's linear motion. Now, turns out that up and down is perfectly good for that. If I throw something up, if there's no wind or anything like that, it's going to come straight down, and that counts as rectilinear motion. And so there's some relationships that you've seen all the way back to Calc 1. Let's get that in the screen. Okay. Integrable. Okay, rectilinear motion just means motion in one direction. Or backward. You can go forward or backward only. So, on a line. So if S, sometimes S is used for position, I don't know why. Sometimes the book uses X as the name of it, X of t. But if S of t is the position or displacement of an object, now, when they talk about position, it has to be from some fixed point, some defined origin that we call 0. So distance from that origin, we can measure it, and that should be our displacement, okay, our position. Right? And there's a relationship, right? Say if v of t, velocity of time t, how does position and velocity relate to each other?
Velocity is the derivative of position.
Mm-hmm. Right. And its derivative? acceleration at time t. Okay. Say, just for the interest of getting some units here, say seconds. Okay, so if our time is measured in seconds, then velocity would be measured in units per second, right? Distance units per second. And acceleration would be distance units per second. Every time I differentiate, it's another rate. Yeah? Okay, and these are related. Velocity at time t is the rate of change of position. And acceleration at time t is the rate of change of velocity. And if we're talking about the rate of change of velocity, v prime will be s prime prime, which is s double prime of t. So these things are all related to each other. And that's in one-dimensional motion. If we have multiple dimensions, then we need vector functions to describe that, right? Yeah, which is awesome, but we're not doing that. All right, so let's look at an example. Let's look at our last example of the day. Oh, but it's a long and... All right, it's a fun one. I like this. All right, so say so on Earth, a woman has enough spring in her legs to jump maximum 2.5 feet tall off the ground, 2.5 feet high. Okay, so that's a vertical leap. All right, and so gravity is the only force that acts on you once you leave the ground, yeah? So the question is, if she were jumping with the same force, or at least the same initial velocity, if she jumped with the same initial velocity from the surface of the moon, how high could she jump?
What's the acceleration of gravity in feet? 32.
32 feet per second, yeah, acted downward. 9.81 meters.
Oh, 9.8.
9.81 meters per second.
Meters.
All right, so we're going to stick with feet. She can jump at maximum 2.5 feet on the Earth. The question is, if she jumped with just as much force, and by force, equal force, we're saying, same initial velocity off the ground. How high above the surface can she jump on the moon? Okay, well that's a fun problem. So this is going to involve some, everything we've talked about with integral, all that stuff. So let's break it down. So on Earth, I need to find some information. We're going to just let and sub E for Earth. That's going to be the acceleration. Okay, so the acceleration after t seconds, and acceleration is measured how?
Feet per second squared.
Right, feet per second squared. I actually prefer to think about it. It's more intuitive for me to think about it. Feet per second. So it's a rate of change of velocity, yeah, with respect to time. But yeah, we often say feet per second squared, but a square second has no physical meaning to me. But so feet per second, great. And just a little subscript means we're on Earth. The velocity at time t on the Earth, this will be velocity after t seconds. And velocity will be measured in just feet per second. You can see how this changes, how the units bear out. Feet per second. Antiderivative is just feet per second. And let's just call h, since she's jumping vertically, h will be the height. Height after t seconds from the beginning of that jump, and that's just measured in feet. So going down the ladder, if you differentiate that, feet, derivative of that is feet per second. Differentiate velocity with respect to time, you get feet per second. Third derivative would be feet per second. That'd be the rate of change of acceleration. Okay? All right, we don't need to go that far. So one thing we do know on the Earth, this is just a constant. The acceleration on the Earth is negative 32 feet per second. Okay, this is what we call G. That constant usually on the surface of the Earth, G. If G is a positive constant, then we just say negative G. It's acting downward. Okay, and we're going to hold on to that value. So the velocity then at time t would be what? Well, if acceleration is derivative of velocity, then velocity is the antiderivative of acceleration, yeah? So what do we get? Negative 32t plus some constant, right? Now, let's think about what this constant would have to be. If we put in after 0 seconds, this would be negative 32 times 0 plus c. So this c value just represents initial velocity. That's what we call initial velocity. So we got negative 32t plus, I'm going to write it just v naught. That's initial velocity. We don't know that, but we're going to want to be interested in that because when she jumps off the surface of the moon, we're assuming she jumps with the same initial velocity. So we're going to be after this guy. All right, and what can we say about the height function?
CT.
Yeah, anti-differentiate this one more time. Negative 32t squared over 2. So that negative 32, that's going to cancel to negative 16t squared plus v naught t plus some other constant. Now, if we plug in the height, if we plug in 0 into this function, this is the height at time 0. We get 0, 0 for that t, and then I just get c1. Well, what do we know about the initial height at time 0? She's on the ground. So she jumps. Stopwatch starts right at the instant she leaves the ground. So at 0 seconds, height is 0. That's the initial height. So we can take this to be 0 because she's jumping from the surface. Time 0 is 0. So the height function is just negative 16t squared plus v naught t plus 0. There we go. Great, so we got all those functions. What do we know? We know that the maximum height is 2.5 feet. But how am I going to find that initial velocity? Okay, we know this will be 2.5 feet. We could solve for t in terms, but we'd have two unknowns, t and v naught. So yeah, we could use that. I mean, that will come into play for sure. But what do you know about, for instance, when she jumps up and she's at her maximum height? What's her velocity?
0. Yeah. Oh, you're right.
So when she reaches her maximum height, her upward velocity is 0. She is, at that instant, her height is neither increasing nor decreasing. So it's a 0 derivative. So the maximum height occurs when the upward velocity is 0. And that gives us something to solve. So I can take my velocity function, negative 32t,
Can you pull it up a little bit?
negative 32t plus v naught equals 0. We set that equal to 0. That's the moment she's at her highest point. And solve this, I'm going to solve it in terms of t. What do we get? Move that term over, divide by 32. I think v naught over 32.
Is it negative 32?
No, I'm going that over to the other
because
side.
it's-
Yeah, the negatives go away. Okay, so that is an expression for the time at which she's at the maximum height. we also know what that maximum height is, so we could use our height function and equate these things.
Why would you use the velocity function to find max height instead of using because it's gonna be different on the moon, never mind.
Oh, yeah, on the moon, yeah, different, yeah, that's gonna be different.
Sure.
We're assuming that the initial velocity, that she leaves the surface is the same.
Sure.
Okay. So the max height is, well, we're gonna use this height function now. Height at, well, this value, yeah? Mm-hmm. So I'm going to my height function. I know it's negative 16 times t squared, and t is v naught over 32. I'm going to use a different color here. V naught over 32 squared plus v naught times t, and that's v naught over 32. And this is the important part. We know something about the max height. We're given that that is 2.5. Okay.
You can divide the 16 out, so.
All right, now we got to solve this for v naught. Luckily for us, that's the only unknown left in that equation. So we can solve for v naught. Okay, and it just gets a little bit better, doesn't it?
Do a quadratic.
It's quadratic v naught, but it turns out it's not so bad. We get negative 16. I'm going to write this as v naught squared over 32 squared. That 32 is getting squared in there with it, right? Plus, and this is going to be v naught squared over 32 equals 2.5. Okay. Now, I'm just going to cancel some things out. I know that there's a 32 squared in here. The 16 is going to cancel partly with one of those. So I'm going to get negative v naught squared over, so imagine in your head there's two 32's multiplied. The 16 cancels with 32 leaves 2, and the other 32 is left uncanceled. Plus v naught squared over 32 equals 2.5. Okay. So this is going to be negative v naught squared over 64 plus v naught squared over 32, and so close to having those as common denominators. Yeah, let's just go ahead and get a common denominator here of 64. So I'm going to write this. We got, I'm going to also, well, it doesn't matter. Negative v naught squared over 64 plus 2 v naught squared over 64 equals 2.5.
V naught squared over 64.
So v naught squared over 64 equals 2.5. This is just a big numerical equation. So v naught equals, I'm going to do two things at once, multiply both sides by 64. 64 times 2 is 128, another half. 160. And we'll just square root that. Square root both sides. Root 160. Okay, so that is the initial velocity. We were able to extract that information. This is roughly, I think I got about 12.65. This is measured in what? Feet per second, because it's a velocity. All right, that's what we needed from the Earth portion of things. Oops, so on the moon, what's going on? Acceleration is different, isn't it? So let's go to the acceleration. I'm going to use sub n for moon. Acceleration at time t, it's no longer negative 32 feet per second, but it's written on the front. What do we got? 5.3. So the acceleration due to gravity on the moon would be 5.3 feet per second squared, but downward. So we direct that force downward. Okay? And so antiderivative of that will give us velocity on the moon at time t. And that would be negative 5.3 t plus v naught, initial velocity, which we just found, didn't we? Okay. So velocity at time 0, everything drops out. This represents initial velocity with which he leaves the ground. Okay, and for now, I'm just going to, well, we'll put it in there, sure. So we got negative 5.3 t plus root 160 is our constant. All right, so height. Height at time t on the moon. Okay, find the antiderivative of this again. Negative 5.3 t squared over 2 plus root 160 t, right? That's a constant, so it gets a linear term, plus initial height. Sometimes initial height is written as h sub 0 or something. At time 0, though, again, initial height is 0. She's jumping from the surface. Okay, so max height, again, occurs when the upward velocity is 0. So we just set the velocity function to 0. Negative 5.3 t plus our initial velocity equals 0, and when that upward velocity is 0, the maximum height of that jump. And we can solve this now for t.
Can you pull it up?
Yeah. All right. I struggle with this thing all the time. Okay. So solving this for t, get that term over there so it's positive, and I think we're going to get initial velocity over the force of gravity, 5.3. Okay, and again, I would just leave it like that, but that turns out to be about 2.386 seconds. So that's a pretty good leap if you can jump from the ground and stay in the air for, coming up on 2.5 seconds. All right, so maximum height. Well, it's the height function when t takes on this value. That's the time at which the maximum height is reached. In fact, let's put it here. 160 over 5.3, just to keep it exact. Another nice way of doing this is use the storage capability on your calculator. Store this as constant, and then you can input it into your calculator. Yeah.
I'm sorry, where did the 2 go? The negative 5.3 t squared over 2.
Oh, you're right. That would be right here. Wait, negative 5.3 t over 2.
Right, and you subtract the negative.
Okay, so when that goes to 0.
And then you multiply the 2 times where it was 160, right? And then you divide it by 5.3.
So you put the 2 in front of the square root.
Yeah, so the 2 should be in front of the 160.
Right, okay, so multiply by 2 and divide by 5.3. But I think that number is right, 2 root 160. Mm-hmm.
Multiply the ball by
Doesn't
2.
the over 2 come in for height, we're solving for
That's
velocity?
the M of t.
Uh-oh, wait, say that again?
Velocity is degree 1, and height is the second degree function.
Oh, yeah,
Now we're
yeah.
solving for the first
Ah, you gotta
degree.
kill me, you're killing me. Okay. Mm-hmm. It is 160 because the velocity function doesn't involve t squared over 2. Yeah, velocity, when velocity is 0. Jeez, sorry, I think hard about these things before I believe anybody. Okay, so we're plugging that value in, but yes, now we're plugging it into the height function. So it's gonna be negative 5.3, I'll put that over 2, and then that's gonna be root 160. This is why you use your calculator. Store this value. That's getting squared, plus root 160 times that t. Okay, and I'm wondering if I brought my, I usually just use a TI-84. But the TI-89 obviously can do the same thing. This value here, root 160, So square root of 160 divided by 5.3. That was our time. 2.3866 seconds. Now, store that. I'm gonna, since that represents the time that this woman reaches the maximum height, I'm gonna store that, alpha numeric, and I'm gonna store it as the constant t. Okay? Yeah, TI-89s, you got that capability as well. You can store that as a constant. So when I plug that in there, I'm just going to call it T. All right. So what I'll say is, yeah, STO. On my calculator, STO is the little function to store that. So I store this as just T. All right, so I'm going to go into the height function, find what the maximum height is at that time. So negative 5.3 over 2 times T, find it again, times T squared, right, plus root 160 times T. And about 15.1.
Wow.
How long does that store last? Like once you turn the calculator off?
No, it's still there. As long as you don't override it with another constant. So, you know, my calculator, I've been using this for, you know, years. A, it's got something in there. I don't know where that comes from. B's got something stored in there. C's got something stored in there. They all got constants in there. It doesn't matter that you got constants stored as those values. If you want to use it again, you overwrite it. You just store as A, and it's replaced.
Wow.
Okay, so about 15.1 feet would be the equivalent jump from the surface of the moon. So there's a little bit of detective work involved in some of those motion laws, sure. Some fun. All right.
Detective work is 2.5 foot vertical leap on Earth.
Yeah.
Some people. You saying that's too much?
That's a lot more than 5.
2.5 feet?
That's
not that high.
That's if you raise your knees.
Yeah, that's if you raise your knees and stop bending.
I'm saying, I don't think any of you can jump on this table without lifting your knees up.
I don't think the table's 2.5.
Oh, 2.5. Yeah, when I was in basketball, yeah. And
Wait, this table
basketball players will
2.5
talk about their
feet.
vertical leap. Michael Jordan had a vertical leap that was over 40 inches.
Yeah, but he was also really tall.
No,
Yeah.
actually
He's also the
actually
one
tall
that-
doesn't have that much to do with the vertical leap.
Spud Webb probably had
Man, I don't know enough about sports, obviously. But this one is
Yeah,
2.5 feet is
like 6.5
2.5 feet is not that, it's not too unlike. I had a 30, I had like a 30, 30. Yeah, that was in high school. Well, I was short, so didn't mean I could dunk, it meant I could touch the rim once in a while. Once in a while. All right, so for next, and by the way, all these, you know, when we do overhead like this, do it together with notes, I'll scan these and post them as well in our files. So, if you, where's our online stuff? All right. Anyway, on my PCC, you can find things like that. I'll also post class notes that we write and whatnot. Yeah, there is going to be homework, so stick around. We still got a few more minutes, so don't make me rush. So, overheads and handouts. Here we go. 4-1, moon jumping. Okay. So you can find those. You can find these overheads, and then I'll take our work that we've done together, scan that, and post it right underneath it. You can find the answers. Okay. I'll also put our class notes. So you can find that. All right. So for next time. All right. Next class, what do we got going on? Stuff. I know that. All right, so homework. for next time, following problems. Section 1.1, numbers 3, 5, 11, 14, 17. Section 1.2, you'll have some of these motion, 1 or 2. Numbers 2, 3, 6, 10, 13, 27, 33, and 38. Also, read over section 1.3. So if you did take Calc 3 recently, you know, some of that stuff that we're going to be talking about, slope fields, is our next item of business. And also, what's due next time is problem set 1. That's not problem set 1, by the way. Problem set number 1 is just the mathography. So you'll be able to find this online. I just realized that I didn't post it up yet, but it will be there tonight. Mathography, you can just find this in my PCC under problem sets. And all it is just a little bit of math, background, letting me know, your math background, where you take your last class, what school you're coming from if you're not from here, what is your major at this point, how much more math you think you have to take, and anything useful that I should know about the way you learn math or what you like to see in class, things like that. Okay, so that will be due next time. I'll put that up tonight before I go, but that will be due. For fairness, yes, returning students will do mathography, but there's going to be a prompt that said, if you took me last quarter, just address this and this.
This isn't a full Saturday, right?
What's that?
Is that the?
It could be on separate sheets. I mean, it could be on just the average.
It's all there.
So it's gonna be like this?
No, there's no math on it. Don't bury me. You have to